Okay, so yes, so today I'm going to be talking about um Polaris and so that our supercomputer at ALCF, our Polaris NVIDIA machine. Um, so there's a link here on the slides to our documentation that has much more in-depth detail than I'll be able to cover today. But anything that you run into issues with or have questions about, hopefully should be pretty well documented in our user guides. Um, Step one, logging in. So hopefully if you're at this point, you should be able to log in and have an account, which is, by logging in, it's just your username at polaris@alcf.anl.gov. The main source of your software that you'll be using are Lua modules, which are aggregated in this soft module files directory. So for example, using the modules from there, you can load the Conda module, which most recently, I suppose, was built at the end of April of this year. So it's relatively up to date, and I think has PyTorch 2 dot something newer than 2.0. So there are a couple more links here. So specifics on queue policies, the different wall times that are allowed for different job sizes and different queues to submit to. So there's a debug queue, a debug scaling queue, and a production queue. Another important point that can be pretty easily overlooked, but we get occasionally tickets from users who are unable to connect to the internet, and through a pip install or however they try to connect, and that's usually caused by failing to set the proxies correctly. So if you put this in your bash RC or startup files, usually this will get sourced as startup, and you shouldn't run into those issues. But again, if you ever run into any questions or see any unexpected behavior, you're always recommended to reach out to us, our support channel at alcf.gov, and that will open a ticket, which we can then work with you to try to get resolved. So Polaris, the system itself. So it is a 560 node HPE Apollo 6500 Gen 10 base system. Each of the 560 nodes has 512 gigs of RAM, DDR4 RAM, with a sort of AMD CPU. Each node has 4 A100 GPUs connected with NVLink, a pair of local 1.6 terabytes on Scratch storage, and Slingshot 11 network adapters for scale out. Yeah, so 2 nodes per chassis, 7 chassis per racks, and 40 racks. Yep. So, oh, maybe I'm just hearing feedback from the podium. Okay. Yeah, this is more of the exact details of what I just said, but so per node, you can see 4 GPUs per node, giving you across the 560 nodes, 2240 total. So I think okay, so then this has some details on the, max throughput for any of the, T-flops for the different floating point precisions. So theoretical, these are theoretical, assuming 100% model or, machine utilization. But they're useful numbers to gauge a sense of how well your application is doing. So if in general, if you're within 10-20% maybe of the theoretical maximum T-flops at a given precision, I would say you're probably doing all right. But it's just, they're sometimes useful to keep in mind or useful to know. And again, all of this information about the specifics of the machine and things are in the user guide documentation. So if anybody has more questions or wants to know more about it, it's all pretty well documented there. So the main point of this talk and what we're going to be looking at today is looking at a simple example of running a distributed training job across multiple nodes of Polaris. And so in order to do that, we will use Python, which then in turn relies on Conda. And so we as ALCF provide a base Conda module that all users can easily load and use.
Just a quick question about the throughput
Please.
on flops. Is there a way to see that easily on the GPUs? You said 80% was a good target for.
I mean, I would say so. There's going to be a lot of things that can impact that. So for example, I would say roughly if you're within 20% of the maximum, I would say when running in distributed fashion. So if you have pretty significant communication and you're still able to hit, a significant percentage of the theoretical maximum, I would say you're doing okay. If you look at your application and you see you're only at, 5% of this, then I would be a bit more, then there's probably something more going on.
Okay, thank you.
Yes. Oh, and so yes, this Conda module we provide comes pre-installed with all of the most popular frameworks. So it has PyTorch, DeepSpeed, JAX, and TensorFlow, all built with MPI, CUDA-aware MPI, which is very useful as well. I mean, I'm getting a lot of feedback from the podium.
Which is 1 minus. Okay, 1 minus. Okay. Oh, that's from 9%. Oh, that's yes. So you can but we also contribute to the sometimes.
Is it possible to mute when you?
It's not just me, right?
Oh yeah, even I'm doing that.
And it doesn't look like I'm able to. I was trying.
So,
oh, there you go. Beautiful. Has me, questioning my sanity briefly. But beautiful. Okay. And if anybody has questions, please feel free to interrupt me. Unmute and just, speak up. Anyway, right. So, yeah, access Python through Conda. Typically, my recommendation or kind of recommended workflow is to always load the base Conda module, and then for any given project you're working on, it's generally a good idea to maintain isolated virtual environments for each one of your projects. So to do that, you would first load Conda, create a new virtual environment at some path, making sure to include the system site packages. So this will pull in libraries from the base Conda environment. And this is nice because it essentially just sits on top of your Conda, and now you're free to pip install, modules and libraries at will, sort of. So, this is just no detail. So I will work through an example towards the end of this that, illustrates all of this. So I'm not going to talk in too much detail. One thing maybe worth bringing up is, we often have users load the Conda module and then automatically jump to trying to clone the base Conda module. So they for their own personal environment, which is fine. But the issue is that it's not only slow, but can ultimately take a lot of your storage, a lot of the storage that you're allocated. And that fills up pretty quickly and can just be a general pain. And unless there's a library that you needs to be installed with Conda, my general recommendation is to use pip as much as possible and kind of work off that base Conda. Just because I've seen a lot of errors and issues that users have ultimately pop up from mismangled paths between Conda and Python, or Conda and pip, and So the Python packaging is not very straightforward for anyone, and so doing things to help simplify it as much as possible, I think, is beneficial.
Just another question about that.
Please, yeah.
So we're using poetry to install, to like do a pip install on top of a Conda environment. Would that be expected to like work relatively okay, or like, what's your knee jerk on that?
Yeah, so I think so. You know, not to get too off topic, but as far as I'm aware, I think poetry is just like a wrapper around. Like, I don't know specifically what it does, but as far as I'm aware, it's essentially like a wrapper around a virtual environment. And so I think it should be, yeah, I think you should probably be able to use it on top of Conda in the same way that you would use a virtual environment. But I don't know exactly how that would end up working. I think that they're pretty good about it. But I haven't tried. I tried it I remember trying it and using poetry briefly a while ago and ran into issues and then kind of abandoned it. But I know it's very popular, and I would have to imagine there has to be some sort of support for, you know, this type of approach. But I'd be happy to talk more about it, like, you know, look into it more for sure.
Thank you.
Yeah, no problem. So I guess we started a bit late. When should I try to wrap up by? I mean, it can be done in 9 minutes if we want, but
Yeah, I think we
I don't
can
know.
a few more minutes. That should be fine.
Okay, I was gonna say I just couldn't remember when I started exactly. So, okay, so for the sake of time, I probably will skip some of these slides. So these next few slides go into details of large language models, how they're trained, you know, kind of state of the art. As I'm sure people are well aware, they are a very active area of research and, you know, commercial business development at this point. And, you know, they are maybe intimidating or, you know, a lot to try to understand for people just getting into, you know, this research. And so what I was going to try to walk through today, and the example is online, so people can feel free to look through it at their own, you know, at their own pace. But we will walk through a really simple example that looks at training a very simple large language model entirely from scratch on a Shakespeare data set across multiple nodes of Polaris. So none of this is important particularly for that. But if you're curious, some of the background and details for you know, how large language models proceed through the development cycle and are ultimately, you know, published and used publicly is a pretty active area of, you know, software development. So there's a lot of, as I'm sure people are probably aware, you know, different APIs, ways of calling and retrieving output from a large language model, and dealing with and connecting all of the necessary infrastructure to make that happen is pretty non-trivial. And so there's a lot of you know, work in getting these things to work correctly beyond, you know, beyond just you having a, you know, typing back and forth with a chatbot. And so my research currently is mostly focused on the large scale distributed pre-training of, so the initial phase, the phase that teaches the large language model to correctly predict the next token in the sequence. And so that is virtually where all of the compute is used in the, you know, LLM development cycle. So at the very beginning, when you have some model with completely randomly initialized weights, it's obviously going to be awful at predicting the next token. And through a very expensive and long pre-training procedure, you essentially train the model to predict the next token. And, you know, as a result, you know, after that, you can then, people are typically what is done is the model is then fine-tuned or trained further to satisfy some, whatever the case may be. So if you're looking at building a chatbot, you would then train it on some, chatbot type data and interact with the model in such a way that, thinks it's a chatbot, essentially. And so there's really all that is to say is that there's a lot more that goes into the development of these tools than people might expect initially. And so with that being said, I will skip most of this. So another maybe important point is when you're training these large language models, very quickly you will want to train models that don't fit in your GPU memory. So typically how, what the general workflow would be is you want to build a model, you scale that model as large as possible on an individual GPU. So you have some memory constraints that are, enforced by the size of your data. And then with the rest of the memory available, you typically make your model as large as possible. And then put identical copies of that model on multiple GPUs and make sure that at each step, each individual GPU gets different data. And so by doing that, that is what's called data parallel training. And that is the most straightforward to implement because the communication is pretty minimal. So all of the GPUs work independently. And at the end of the backward step, basically all sync up on their gradients and propagate the weights out to everyone, but has overall the least amount of, intercommunication. And so it's most easiest to get set up and straightforward. Going beyond that, you'll eventually reach a point where your model is no longer able to fit in your GPU memory. At which point you're only, so there are a few things you can do then. So for example, DeepSpeed offers various stages of it's called zero offloading. But the idea being that they offload either model states, parameter weights, or optimizer states, and recompute them as needed. And by doing that, they're able to free up additional memory for model weights. So there are a few other tricks you can get around it, you can use to try to get around it, but at the end of the day, eventually your model will be too large to fit on a single GPU. At that point, you have to resort to either pipeline or tensor parallelism, in which each tensor gets split up into multiple chunks and is generally a much more complicated procedure, because at each intermediate point in your forward calculation, there needs to be communication between GPUs in order to make sure that all of the tensors they need to carry out their part of the calculation, are present. So this is another very active area of research, and something that people are, working on, very actively, including, people here at ALCF. So the example we're going to look at today is pure data parallelism, obviously, since it's the most straightforward and easiest to understand. This is more details that don't matter. So there are maybe a few prerequisites before we launch the actual training. So there's this library that I wrote and maintain called Easy Peasy, that we'll use for part of this. So it's on GitHub, you can see there. And it really is I built it originally because I was tired of always having to do these same MPI for pi initialization calls and things and different applications. And so I made a little library that simplifies all of that for you and has some additional kind of nice features that are useful for running at ALCF specifically. So this is all of this code here is the history. Basically, I ran through this example this morning just to make sure it all worked. And so this is like the, shell history from me doing that. So, just for sanity's sake, navigate into a, temporary directory, completely isolated, and make fresh clones of the repos we're going to be using. So first, like I mentioned, clone this easy peasy library, which has utilities for just, initializing PyTorch and things like that. And then this wordplay library, which is another library that I've written and maintained that contains a very minimal implementation of a large language model, and has the code for, running and training that. So clone these two repos anywhere you like. Once you've done that and cloned the repos, there's this utility utils.sh script in easy peasy that you can source and will then provide you with functions for setting up Python and setting up at ALCF. So if you source that utils.sh and call this easy peasy setup Python, you can see it will print out that there's no conda in your environment. So depending on the system, so this will work across Polaris or any of the machines at ALCF, but it will correctly set up conda and load the right module needed to do that. Then it'll load and activate that conda module. On top of that, it will then build and activate a virtual environment with name matching the conda name in your Active Directory, and then activate it. So basically what that does is completely takes care of the conda and virtual environment setup for you. And then this easy peasy setup ALCF does some nice little tricks. Essentially, if you are on a compute node, it will identify the node ID or the PBS node file that contains this host you're on. From that host file, it will count the number of lines. Basically, this node file is formatted with one host per line. And so by counting the number of lines, you're able to determine the number of nodes that your job has. So in this example, it was just a single node. And then using the number of nodes, in combination with the number of nodes and the number of GPUs on each node, it's able to determine the total number of GPUs. The total number of GPUs. So in this case, one host, 4 GPUs per host gives you a total of 4 GPUs total. And it basically combines all of this information to build a MPI exec command that you can then use to launch Python or whatever the case may be across all of the workers in your job. So I'm already kind of pushing on time. The next few slides kind of walk through the installation and running process. So once you've ran these setup functions, you now have a virtual environment built on top of the conda and this alias launch you can use to launch with MPI exec. Next thing you have to do is install the Python libraries. Yeah, sorry. I can tell if people are trying to interrupt me from the podium or if it's just feedback. But if you're trying to interrupt me, you're going to need to be a bit more assertive or like louder, but maybe not. Okay. So I'll wrap up in a couple minutes. Right. The next step is to install the Python libraries. So in particular, there's easy peasy, which has the distribution backend, and this wordplay, which has the language model implementation. So that's very straightforward and will install. There's a recent upgrade to weights and biases on Polaris that breaks things. If for whatever reason you try to run and you get a weights and biases error, it's likely because the conda is using an older version. And so if you just do an upgrade, that'll fix that. And then an easy way to test that you've installed this easy peasy correctly and gotten everything else set up correctly you can check and make sure that you have this launch alias set in your set in your current environment. Look at your Python, make sure it's pointing to where you expect it to be. And then you can launch Python, and in particular, this test dist module from Easy Peasy. And this is just a very simple test to make sure that all of the distributed communication setup works correctly and everything. And then basically runs through training like a very simple, 5-layer multi-layer perceptron. Just on randomly, generated data. And then it prints some stuff, does some little text plots, yada yada. It's kind of nice. But this is a useful test, just to make sure that your Python's set up and everything else has been set up and installed correctly. To profile, it doesn't matter. This is the video of me interactively working through everything I just said. And then the training of the language model. So the rest of the details are in here. It's pretty straightforward once you've installed the libraries and everything. The only thing you have to do is prepare this. So for this example, it downloads and tokenizes the contents of Shakespeare's work, and tokenizes it into 100,000 tokens. And then you can, with the data in place, we can launch the wordplay module using the DDP backend, evaluating the model every 100 steps using the Shakespeare data we just set up with BF16 data type, batch size 64, sequence length 1024 for 1,000 iterations, printing every 10 steps without compilation. And you can see that it'll go through the setup and everything, print out some information about the model, and so on, and a little legend about what all of the things mean, and then it'll basically run through the training. And you can see the main takeaway being that first initially you can see it obviously just outputs complete garbage. This is obviously incoherent. But then as the training progresses, you can start to see that it looks a bit more like, how Shakespeare would write. And this was, only like a 5-10 minute job, and so I killed it. But if you were to let it keep going, this would get better and better, and eventually, talk just like Shakespeare. And this is just a video of me walking through those previous steps. So you can see it yourself and see what it looks like. I don't know why, for some reason, these videos seem to get like bumped down, and you need to like reload it and move it around and it'll fix it. But yeah, I guess, so that obviously I ran through that at the end pretty quickly. If people have questions or, are trying to work through this themselves and run into issues, I'm always around and would be more than happy to hop on a call or talk more about it with anybody if they have questions. Yeah, otherwise, thank you everyone for listening. And yeah, let me know if there are any questions if we have time.
Yeah, well, thank you, Sam, and I know Easy Peasy is pretty fantastic. You helped us debug some of the best stuff when we were at the hackathon.
Thank you. Thank you.
I guess one question here is, would you see like because like Easy Peasy seems like a pretty like great collection of like scripts to launch things. Do you see this as like a good way to basically like, I want to jump on a machine and run, as opposed to like one of the Hugging Face frameworks or so on, or more as like a diagnostic tool?
I would say I'm obviously biased having built it. And yeah, I would say it's so I would say it's nice because so it really only depends on PyTorch. If you have deep speed installed as well, it can take advantage of it. But at the base level, all it really needs is PyTorch and MPI for Pi. And so I'd say it's maybe a bit more generic than like, which I also do appreciate the Hugging Face libraries, and I wouldn't want to say that like this is easier or anything, because they obviously put a lot of effort into those things. But it really, it really was born out of me. Every application I worked on, I would start, have to import MPI for Pi, just, broadcast the master address to all of the workers. And it's this like, 20 or so lines of code that I found myself copying and pasting into every application I was working on. And so at one point it was just like, this is much easier for me long term if I stay, yank this out and put it somewhere else that I can just always pull from. And so it's built and I've added more things since then, but yeah, it's really about functionality for me at the end of the day. Something that works and that I don't have to think too much about. But if anybody ever has suggestions or like, this could be better, or have you thought about this, or I would be more than happy to talk about those things anytime. So sorry, that was like a roundabout not answer to your question.
Thank you. But it definitely was helpful. I think we're about to switch over to the hands-on session, but I think I can get some
Sure.
question about singularity of this.
Absolutely, please.
Thanks, Sam.